The deepest hole humans have ever drilled reaches about 7.5 miles down. That sounds impressive, until you realize the center of the Earth is about 4,000 miles down. That drill hole barely scratches the surface, less than 1/5% of the way to the center. So how do scientists confidently describe layers we've never physically touched, let alone seen? The answer involves earthquakes, and a clever kind of listening that works a lot like an X-ray. And it includes a brilliant discovery made by a scientist who noticed something that wasn't supposed to be there at all. Let's get into it. The main tool scientists use isn't a drill at all. It's earthquakes. Every earthquake sends powerful waves of energy traveling through the entire planet. Seismographs positioned around the world detect and record exactly when these waves arrive. By carefully studying how these waves travel, scientists can essentially build an image of Earth's hidden interior. It works surprisingly similarly to how doctors use an MRI or CT scan to see inside the human body, instead of light or radio waves. Though, scientists are reading the echoes of the planet's own earthquakes. There are two main types of waves involved, and they behave in genuinely different ways. P waves, short for primary waves, can travel through solids, liquids, and even gases. S waves, short for secondary waves, move differently and can only travel through solid material. That single difference turns out to be one of the most powerful clues in this entire investigation. If S waves suddenly stop appearing somewhere, that's a strong sign they've hit something that isn't solid. In the early 1900s, scientists noticed something strange while studying earthquake recordings worldwide. On the opposite side of the planet from a major earthquake, S-waves simply weren't showing up at all. This missing region became known as the S-wave shadow zone. Since S-waves can't travel through liquid, their disappearance strongly suggested something liquid was blocking them. This was some of the earliest solid evidence that part of Earth's core isn't solid rock at all, but liquid. P-waves told their own separate, equally revealing story. Since P-waves can travel through liquid, they did pass through the core, but they came out bent in unexpected directions. This bending created its own distinct gap, called the P-wave shadow zone, at a different specific angle range. By carefully measuring the exact size and shape of both shadow zones, scientists could calculate the core's approximate size. It's a remarkable example of using absence, missing data, as genuinely powerful scientific evidence. Here's that brilliant discovery I mentioned at the start, and it happened in 1936. A scientist named Inge Lehmann was closely studying earthquake data, including recordings from within the expected shadow zone. She noticed something that shouldn't have been there at all, faint P waves showing up inside the supposed shadow zone. Her explanation was genuinely elegant. There must be a distinct, solid inner core, nested inside the liquid outer core. Waves reflecting off that unexpected solid inner boundary explained the faint signals she had detected. Her 1936 discovery has held up remarkably well, confirmed repeatedly by generations of later research. Seismic waves aren't the only clue, though. Simple density math also plays a genuinely important role. Scientists can calculate Earth's overall average density using its known mass and volume. That average density turns out to be notably higher than the density of typical surface rocks alone. That strongly implies something considerably denser must be concentrated somewhere deep inside the planet. Iron is a natural, well-supported candidate, since it's dense, relatively abundant, and fits the evidence well. There are two more genuinely clever sources of evidence supporting this iron-rich picture. Certain meteorites are believed to be fragments of the shattered cores of ancient, destroyed planet-like bodies. These iron-rich meteorites offer scientists a rare, direct physical sample of what a planetary core might actually contain. Earth's magnetic field provides another major clue entirely. It requires a very specific kind of core to exist at all. Generating that field requires a liquid, electrically conductive layer that's actively moving and circulating. A liquid metallic outer core fits this requirement precisely, reinforcing the seismic evidence we already covered. Scientists have even found ways to recreate core-like conditions directly in a laboratory setting. Special devices called diamond anvil cells can squeeze tiny samples between two diamonds at incredible force. This lets researchers test how materials like iron actually behave under Earth's core-level pressure and heat. These experiments have consistently matched predictions based on the seismic wave evidence collected separately. Multiple completely different scientific methods keep independently arriving at the same overall picture. Modern researchers have gone even further, combining data from thousands of earthquakes into detailed 3D models. This technique, called seismic tomography, works a lot like combining many individual CT scan slices into one image. It reveals not just simple layers, but genuine variations in temperature and material within those layers. Some regions of the mantle show up as unusually hot or unusually dense compared to their surroundings. It's given scientists a far richer, more detailed picture than the simple layered diagrams from a century ago. Quick pause before we continue. Take a guess. Do you think scientists need a massive, record-breaking earthquake to study Earth's deep interior? Not necessarily. Even moderate earthquakes generate more than enough usable wave data for detailed analysis. Modern sensor networks are sensitive enough to capture genuinely useful signals from many routine seismic events. Let's clear up a few common myths before we wrap up. Myth 1. Scientists have actually drilled all the way down to study Earth's core directly. Not even close. The deepest hole ever drilled reaches only a tiny fraction of the way toward the center. Myth 2. The inside of the Earth is just one giant ball of flowing lava all the way through. Not accurate. The inner core is actually solid, despite intense heat, due to the enormous surrounding pressure. Myth 3. Seismic waves can only reveal information about earthquakes themselves, nothing else. Not true, as we've covered extensively. They reveal enormous amounts of detail about Earth's internal structure. Myth 4. Scientists are still completely uncertain about what Earth's core is actually made of. Not accurate. Multiple independent lines of evidence consistently point toward a primarily iron-nickel composition. Myth 5. The mantle is just a simple, uniform layer of rock with no internal variation at all. Not accurate. Modern seismic tomography reveals genuine temperature and density variation throughout the mantle. Myth 6. Only massive, record-breaking earthquakes are useful for studying Earth's interior. Not true. Even moderate, routine earthquakes provide genuinely valuable, usable seismic data. Let's wrap up with a few fun extra facts. The inner core is estimated to be almost as hot as the surface of the Sun, despite being deep underground. Some research suggests the solid inner core may even rotate at a slightly different rate than the rest of the planet. This remains an active, ongoing area of genuine scientific research and occasional debate. Every major earthquake anywhere on Earth adds more usable data to this enormous, ongoing global picture. It's a genuinely remarkable case of turning a natural disaster into a powerful scientific instrument. Okay, let's bring this all together. Scientists study Earth's interior using earthquake waves, since no drill can reach anywhere near the core. S-waves revealed a liquid outer core, since they can't travel through liquid material at all. P-wave bending revealed the core's size, and in 1936, Inge Lehmann discovered the solid inner core hiding within it. Density calculations, meteorite evidence, Earth's magnetic field, and lab experiments all independently support this picture. Together, these completely different methods all point toward the exact same conclusion. All from careful listening to a planet that's been quietly revealing its secrets the entire time. If this answered a question you never knew you had, that's exactly what this channel is about. So if you enjoyed this, hit subscribe so you don't miss the next one. It genuinely helps this channel grow, and it takes about 2 seconds. Drop a comment and tell me which part surprised you the most. Was it the shadow zones? Inge Lehmann's discovery? Let me know. And if you like this video, go ahead and tap that like button. It's a small click that genuinely helps this channel keep growing. There are hundreds of everyday questions just like this one waiting to be explored. Things about our own planet you've never actually stopped to question. That's what this channel is all about. Toggling your curiosity on, one question at a time. One more thing before you go. Tap that notification bell too, so you actually see it when the next video drops. Next time, we're tackling why flamingos stand on one leg for hours without falling over. It's a surprisingly clever energy-saving trick, and you will not guess the mechanism. I'll see you in the next one.